what you're finding here today is so there is a system which is the system is given here. We are going to solve this numerical. It's a big numerical, but it is not difficult. Only the solution look big. So here it's a mechanical system. The question is we are supposed to find out the FV analogy of this big mechanical system. So what is this mechanical system? You can find out the first one, that is K1, B1 and M1. This is the first system or first loop, as you can say, and force is applied to the M1. So this will be the first loop. Generally second loop is connected to the first loop below, but here the second loop is connected with the first loop inside it. So it is also exactly the same numerical we have solved previously. So this is K1, B1 and M1, and previously what we found was this K2 and M2 was outside. Now this K2 and M2 is inside, that's all. And there is another force here. So what we are finding is this B2 is very much important to understand, that there is a force here, there is a friction force here, that is between M1 and M2 there is occurring a friction force. So whenever you are talking about K2, whenever you are talking about M2, what all forces are there? So whenever you are talking about M2, there is K2, there is B2, and how this B2 and K2 is connected. So B2 and K2 will be connected to the node X1, and this B2 and K2 and M2, they are also experiencing another displacement which is called as X2, which is not shown here. Okay, so this is the only thing we have to understand, because in this case this K2 M2 is inside this M1. Okay, so whenever I show you the free body diagram, so the free body diagram you are supposed to draw next. Whenever I show you free body diagram, you'll understand, or from this diagram also. So this is the basic diagram given. So here X1 is given but X2 is not shown. Okay, so B2 is there, there is a friction force between M2 and M1, that is shown here. So this is a basic diagram. As soon as I show you this, I think it will be a lot easier for you. So what all things we are finding here? The same thing, that is there is K1, there is B1 and there is M1. This is the first loop which is connected to force Ft. So Ft is connected to M1, so that will be the equation where Ft, M1, K1, B1 and all those things are linked. Now this K2 is common for X1 and X2, and with X2 there is connected K2, B2 and M2. Okay, so it is written here the minimum number of displacement must be equal to the number of masses. This is one thing we are supposed to know. So in the previous diagram here only X1 is shown, but we are finding there are two mass. So as masses are the main thing which are moving, everything else is moving, but for mechanical system the rule is the number of displacement or number of equations should be equal to the number of masses. So as here there are two masses, there should be two displacement, there should be two equations, and from those two equations we can find out the relationship between transfer function. So x1 is by fs, it can be a transfer function. X2 is by fs, it can be a transfer function. So last day also the same kind of numerical used to happen. I told you that you practice. So today I have taken this from a book, and in between I have put my solution. So book is also having its solution, so I'll be posting all this printed things today, tomorrow. So book solution is also there, but they have not found the transfer function. But in the exam generally we find transfer function. In this book solution they have written all the time domain equation. So what we'll be doing is we'll be finding the transfer function of the system, that is x1 is by fs, x2 is by fs, what all thing, how to find that. Then whatever equation we write in terms of dx1t dt or dx2t dt, so whatever time domain equation we write here, there will be two time domain equation, one at node x1, another at node x2. Then we are supposed to find out the RLC FV, that is force voltage equivalent of those equations. And whatever equation I have written and whatever equation are given in the book, they are different, but both are correct. You can find out. So I have directly written the equation not in time domain. So I have drawn the equivalent of this thing in FV, that is whatever is the RLC equivalent of this. So first I have found this, I have converted this thing into Laplace, then I have directly found its equivalent RLC circuit. So all those things I'm going to show you shortly. Just check. So you have to remember this diagram. So if you want, you can take a screenshot. So just I'm giving you 10 seconds time, just take a screenshot of this, so that whenever I go to the next slide, you should be able to understand it. Okay, so understand this K1, B1 and M1, this is the first loop, Ft is given to the first loop, and this B2 and K2, this is the link between X1 and X2. So this B2 and K2, they are common for X1 and X2, and x2 m2 is there. So exactly this kind of free body diagram. So name this in the exam also. Whenever you are drawing it, name it as free body diagram. So what you are finding is with ft, m1, k1 and b1 are connected. So I will going forward and backward just to show you the diagram. So just check with ft, m1, b1 and k1 are connected. So here you are finding m1, b1 and k1. So b1 is nothing but the damper whichever is shown here in the previous diagram. K1 is the spring, m1 is the mass. So there are these four elements which are directly connected to x1t, and there are two more elements. So whatever k2 and whatever b2 you are finding, that is also connected to x1, but that is common between x1 and x2. So exactly this kind of numerical many we have done, so there is nothing to get scared of. This numerical will be big, but it is not difficult. Only you have to keep on following the basic rules. So this b2 and k2, this is common between x1 and x2, and there is another point x2. From that x2 point, there is a mass m2. So I think whatever list of numerical madam has forwarded in your group, that is ABCD, the common control system group, this numerical is there. So I'm giving you the solution for that. It is from the book of Ganesh Rao. So that book is having a lot of mistakes. So many numericals are solved, but a lot of mistakes are there. Anyways, I'll be giving you all the solution from that book. So if you find any mistake, please report it to me. Okay, so this is the block diagram. This is the free body diagram. What we find here. So now we are supposed to write the equation. So you find it is m1 d2 x1 dt2. So this is m1 d2 x2 dt2. So is equal to ft. So here you see that this ft is small ft, because this ft is nothing but a force, and the force is a time domain. So this force is changing, it's varying. Likewise, whenever we write sinusoidal waveform vt for some kind of AC analysis, we write it small vt because it is instantaneous voltage. Okay, samely here also it is written as ft. So it is there, input ft. So d2 x1t dt2 into m1. So this is the thing we are finding. Second is k1 x1t. So k1 x1t. So they are not writing x1. So this is there, but you have to understand it. So only x1 is written. That is not a right thing to do. So what you do is d2 x1t dt2 k1 x1t and all. So in exam you will be solving one numerical. So please write x1t. Next is b1. So this b1 is nothing but the damper. Okay, so this is b1 dx1t dt. So you are finding this b1 k1 m1, they are connected to the ground. So they are connected to only one displacement, which is called as x1t. Now there is coming components, that is this k2 and b2, they are actually connected to both the displacement x1 as well as x2. So as you are writing from the node of x1, what you have to write is b2. So b2 is nothing but common between x1 and x2, but as you are writing node equation for x1, so what you should write is b2 d dt of x1 minus x2. So that is what they are writing, b2 dt d dt x1 minus x2. Okay, and samely k also you should write k2. So this should be k2 into x1 minus x2. So this thing. So this k2 x1 minus x2 and b2 ddt x1 minus x2, these two are the elements which are common for x1 node and x2 node. So this is very simple. Every numerical is the same way we are doing since long. Only this diagram, this basic diagram is little different. Hence, I am taking this numerical. Otherwise, when you draw this free body diagram, then everything is in your domain. So there is nothing new in this. Okay. So whatever is the input voltage Ft, so that is equal to mass M1, K1 spring, B1, that is the dashpot or damper. Then there are two components which are common to x1 node and x2 node. It is given by this. Don't look at what is given below. So don't look at it, because now I am going to go to my notes, and you have to remember this diagram. You can take this screenshot as well, and the same equation I'll write. And for loop 2 what will be there? So for loop 2 it will be m2 d2 xt dt2. That is the first thing. Second will be k2 into x2 minus x1, and there will be b2 d dt of x2 minus x1. So I'll repeat. For second loop, it will be m2 d2 x2t dt2 plus k2 into x2 minus x1 plus b2 into d dt of x2 minus x1 is equal to 0. Because whenever you are writing for equation for node x2, there is no input connected here. Okay, so that equations will be saying. Now come to my notes and check how we have found the function. So last day also I was telling you find this, find that, do it this way, do it that way. but I thought like it will be better if I show you one equation. So there's the same first equation I have written, so you won't have to worry about it. I guess it is visible. Okay, anybody please confirm it. Darkness is not very much, so anybody please confirm if it is visible at your side.
Yes, sir.
Okay, so thing is visible, so I can go ahead. So don't worry about the equation. So equation and circuit system you match later on. This is correct. I'm only show you what is the process. So more than numerical, you have to understand the process. So this is M1 D2 X1 to D2. That is the mass in the first side. So this diagram you have to remember this diagram. So this is M1, K1, and B1, all related to X1. So M1 D2 X1 to D2, K1 X1, B DX1 T DT. Then there is common elements, that is k2 x1 minus x2. So you're writing node equation at x1, that's why it is x1 minus x2. Then b2, so k2 and b2 are the common elements. So this is b2 d dt x1 minus x2 is equal to ft. Now you have to take the Laplace transform. So this ft becomes fs. Now this m1 becomes m1 s square, because this is d2 x1 dt2. K1 x1 becomes k1 x1s. Now the mistake is I have not written x1t x1t. So all this x1t and x2t had to be written, then only you can write x1s and x2s. In some book you can find out they are writing directly k1 capital x1. And another difference is here it is everything small, because this is time domain. After Laplace everything should be capital. So this is k1 x1s plus b1 s x1s, because here this is single derivative, here this is double derivative, that's why a square has come. Here this is single derivative, that's why s is coming. So whenever there is differentiation, it should be multiplied by s. Initial conditions are 0. Whenever it is integration, it should be divided by s. Now this is k2 x1 minus x2. So this is k2 x1s minus k2 x2s. So I have multiplied and separated and taken Laplace transform. So this k2 x1s minus k2 x2s. So this is k2 x1s minus k2 x2s. Actually, what I have done in this Laplace is I have separated out the x1 term and x2 term. So one step I have done less in this. So in this is b2s x1s. So this is b2s x1s, and this is b2s x2s minus likewise. And next step I have separated out x1s and x2s. Okay, so very fast I have done it. And then check the second loop. Second loop you found that k2 and b2 they were common between x1 and x2. So now I am writing equation for node x2, that's why x2 minus x1 has come for k2. b2 also ddt of x2 minus x1 has come, because now I am writing node equation for x2. And here also you have to write m2 d2 x2 dt2. Only change you have to do in the exam is d2 x2t, k2 x2t, x1t, and all those things you have to write. Now take the Laplace transform in both the sides. So very important thing is this case there is no input here. So this is 0, because if you see the second loop, second side, there is no input here. Okay, so that's why this side it should be 0. Same numerical we have done many times. So whenever you are writing loop 2 equations, you are finding that right side it is 0. And now take the Laplace both the sides. So this becomes m2s square x2s, this becomes k2 x2s, this becomes b2s x2s. So another one step I have done less here. So in this Laplace only I am separating out x2 and x1. So right side this is k2 x1s and b2s x1s. Then I have separated x1 and x2, and I'm representing directly x2 in terms of x1. Okay, somebody wants to represent x1 in terms of x2. So in that case you can write x1s is equal to this one, that is m2s square plus k2 plus b2s divided by k2 plus b2s. So x1 can be represented in terms of x2, or x2 can be represented in. So this equation number 3, we can represent x1 in terms of x2 or x2 in terms of x1. That depends what transfer function is asked. If the transfer function is asked x1 by fs, so in that case we have to remove the x2 term. In that case we will do what? If x1s by fs is asked, in that case we will represent x2 in terms of x1, and this we will substitute in the first equation, because from the first equation we have to remove x2. That means the x2 has to be represented in terms of x1. So from the second equation, Laplace transform, this kind of relation, kind of a ratio kind of relation we find between x2 and x1. And if x1 by fs is asked, we will replace x2. So in that case, this is correct. If x2 by fs is asked, in that case, what we have to do is in the first equation, that is this equation, you have to replace x1 in terms of x2. So in that case, what we will write below, what we will do is x2 is equal to m2s square plus k2 by b2s divided by K2 B2S into X2S. So X1 we will represent in terms of X2 then. So in this case, what first we have done is we have represented x2 in terms of x1 because we will find x1s by fs. So in this case, we have done that, and this value number 3 we have substituted into equation 1. And if you are doing that, so f is equal to x1 is this term, first term is same, so you can find what is the equation 1. So this is the first term, and second term there is the x2. So this x2, what we will do is this x2 we will represent in terms of x1. So this is after substitution what we get here. Now what we are finding is x1 and x1 we can take common. So this term, so this big term minus this term. Okay, so this will now become in the denominator. So finally what we are writing is x1 is by fs. So if you are taking all x1 common and then x1s by fs, if you are doing, the whole term goes in the denominator because x1 is at the numerator. So in this case what we are finding is the ratio of so there are two displacement x1t and x2t, or x1s and x2s. So there can be two transfer function possible. One is x1 is by fs. This is the way we have found it. Now if you have time, then you go on simplifications. How to do the simplification? This term m2s square plus b2s plus k2, it will go in the numerator. This term will get multiplied with the first term and minus k2 into b2s. So main important thing is you have to check is here there is a square. Okay, here there is a square, and whenever you are multiplying it with this term, so there will come s raised to 4 in the denominator. And if you see the diagram, this diagram, how many energy storing elements are there? So you will be finding that there are 4 energy storing elements. So what are the energy storing element? M1k, M2k. So these are the energy storing elements. So as there are 4 energy storing elements here, here also there will be 4 energy storing element in the system. So the transfer function denominator will be having s raised to 4, because this m2 square and this m1 square, if you multiply, it will become m1 m2 s raised to 4. So s raised to 4 is the degree of characteristic equation. That means this is a fourth order system. So this is how x1s by fs is found. Now if somebody asks that I want x2s by fs, okay, because there are two displacement, hence both the transfer functions are possible. So what you do is in that x1 is by fs, whatever just now we have found, substitute x1 is equal to this. Okay, so in the equation number, so in the previous page there is a third equation. So third equation is nothing but relationship between x1s and x2s. So here this is the ratio form, relationship between x1s and x2s. So just before I have explained to you, x2 can be represented as x1, x1 can be represented as x2. So next page toward the top, I have represented x1 in terms of x2. That means x1 is something of x2, and the same thing you substitute in the x1 is by fs. So in the x1 is by fs, what is already found, so this thing is already found. What I have written is in place of x1 in the numerator, I am writing x2 into m2s square plus b2s plus k2 divided by b2s plus k2. Now this whole thing you can just give a short name as as or something. Okay, so in that case your calculation will become much easier. So x2s into as you can write down. Okay, and then this is this divided by fs. Now what happens is this thing comes here at the denominator. So in the next step, so this part remains same. Whatever is the transfer function you have found, that is x1 is by fs, the denominator part remains same, the numerator part remains same. Now what we are doing is change is coming in the numerator of x1 is by fs, because now x1 we are writing in terms of x2, and finally we will represent x2 is by fs. So what will happen is this thing will come in the denominator. So whenever this thing comes in the denominator, the flip of it will come in the numerator. That means this b2s will go at the numerator and m2s square will come in the denominator. So x2s by fs will be this term, that is m2s square plus b2s plus k2 at the denominator and b2s plus k2 at the numerator, and denominator will remain same. So for both x1s and x2s, the denominator will remain same. If you check, this is the equation, this was the equation for x1s by fs. So this was the denominator. In x2s by fs also denominator remains same. Only x1 by fs, the numerator is 1, and x2s by fs, the numerator is b2s plus k2 divided by m2s square plus b2s plus k2. This is the only difference. Now next what we are going to say is the circuit free body diagram. So you can call it FBD. Okay, so in very short I have done the FV equivalent. Okay, in you can do this also. So I told you there are two kinds of numerical possible. So this is the first kind where first I have found the every transfer function and everything related to the mechanical system, and finally I am converting the mechanical system into equivalent electrical system and writing the state equations. So this is one thing that we can do. Another thing is this whole mechanical the mechanical equations or mechanical analysis we are not supposed to do. So in the first itself, after you draw this, so the question is arranged like that. After you draw this, directly you have to convert it into equivalent FV, and after you do FV, then you are writing the FV equation. So whatever is Fs, that becomes Vs. So this is one loop equation, that is Vs Q1s Q2s, and this is the outer loop equation, that is Q2s and Q1s, where Q is the charge. So though I have written I1 and I2, but S into Is is equal to Q1s, because we know that Qt is equal to dit dt. So Q1 t is equal to di1 t dt, and Q2 t is equal to di2 t dt. In that case, S into I1s is equal to Q1s, S into I2s is equal to Q2s. So directly you can write down these two equations. Okay, so whatever is the M1 and M2 equation. So previously, whatever equation you had found, equation 1 and 2. So these two equations. So in this equation, Fs directly you substitute as Vs, x1 you substitute Q1 as, M1 you substitute L1, K1. Okay, so K1 you can substitute as C1, and C1 will be equal to 1 by K1 in the next. So value if K1 is given suppose 5, C1 has to be substituted as 1 by 5, that is 0.2. And B1 and B2, that will be R1 and R2, and K2 will be 1 by C2. Like this. So and accordingly here C1 will be 1 by C2, this B2 will be R2, and accordingly we can substitute the equations. So this is actually if V equivalent first equation. Second equation is also like this. This is for loop 2. So I have shown the circuit in the next page. So here also it will be M2. So here you can say L2 and D2, Q2, DT2 accordingly. So directly no need to write the time domain equation. Directly you can come to the Laplace domain equation, because Laplace domain equation will give you the transfer function in Laplace domain. So you have to draw the electrical equivalent circuit and directly go to the Laplace domain equation. So the same thing I have done in a very small place. Actually numericals are very small if you know how to solve it, and it is repetitive. So what was the directive? Directive was, whenever you are finding FV analogy, in that case all the series become parallel and all the parallel become series. So in this case you are finding FT, so that becomes VT, and M1 K1 B1. So M1 becomes L1, K1 becomes C1, that is 1 by C1, or B1 becomes R1, so they becomes in series. So L1 C1 and something called as R1. So this R1 can be drawn in the top also. So this M1 become L1, K1 becomes C1, and B1 becomes R1. So whenever K1 is becoming C1, but if M is 2, L will be also 2. But if K is 5, then C will be 1 by 5, that is 0.2. That is the only thing you have to remember. If B is 10, then this R also will be 10. Okay, and if F is 100, this V also will be 100. So only change comes in case of the value of C1. So we'll write C1, but whenever writing the actual value of it, we will write this equal to 1 by K1. So that is the first part. Second part is B2 and K2. So these two things are in parallel and they will appear in series. And again the series arm will come in parallel, because here this is a series thing. So here they will come in parallel, and B2 and K2 they are in parallel, so they will come in series. So this B2 becomes R2 and K2 becomes C2, and the value of C2 is equal to 1 by K2. Finally this M2, the M2 will become L2. So what you have to practice now is how to convert any mechanical system into equivalent FV system very fast. Okay, so very fast, as soon as I give you this free body diagram, very fast you should be able to convert it into equivalent RLC circuit. So what I have written is L1 is equal to M1, L2 is equal to M2, R1 is equal to B1, R2 is equal to B2. C1 value, okay, C1 value should be 1 by K1, and C2 value should be 1 by K2. And you can write I1, but I'm writing the Laplace domain equation directly, so no need to write I1. Directly substitute S I1s is equal to Q1 and S I2s is equal to Q2. So directly you can write down this equation. So Vs is equal to, previously we used to write I1s into L1s plus R1 R2 plus 1 by Cs and all those things. So don't write that. Directly substitute from the previous equation. So F becomes V, whatever was x1 that becomes q1, m1 becomes l1 square, and this was b1 plus b2 that becomes r1 plus r2, and this was k1 plus k2 that becomes c1 plus c2, and this was q2s, and sorry, this was x2s, so that becomes q2s, and this was actually b2s plus k2, so that becomes r2s plus c2. So just you have to do the equivalence. Whatever was the value of b, that will become r, whatever the value of k, that becomes c, whatever the value of m, that becomes l. So this is the equation a, that is the for fv analogy, this is the equation a. Now in this case I can ask you find q1s by vs, that is the transfer function of this first loop, or I can ask you q2s by vs. Okay, that is a charge in the second loop or charge in the first loop. So charge is the output and voltage is the input in this case. Whatever is the equation of the second loop, so second loop, as we have found in the previous case, so q2s, it was x2s, it was m square, m2 square, so that becomes l2 square, it was b2s, that becomes r2s, it was k2, that becomes c2, and we know that c2 value is 1 by k2, minus it was x1s, so that becomes q1s, and it was b2s, that becomes r2s, plus k2, k2 becomes c2, and we know that c2 is equal to 1 by k2. Now how to find q1s by vs and q2s by vs? Exactly the same process which I have explained just before. That is, from this second equation, b equation, you have to represent either q1 in terms of q2 or q2 in terms of q1. If you are representing q1 in terms of q2, the whole thing you have to take to the right, then write q1 is equal to q2 into this divided by r2s plus c2, and that value of q1 you have to substitute here. If you're doing that, what remains is vs, q2s and q2s. In that case, you have to take all the q2 in one side and you can find out the relationship between q2s by vs. Somebody wants that I want a q1s by vs. That means from this equation you have to find q2 is equal to q1 is into r2s plus c2 divided by l2s square plus r2s plus c2. So q2 you have to represent in terms of q1 then. And after you are doing that, then you have to substitute that value of q2 in the previous equation. That means whatever is the q2 that will be represented in terms of q1. So this first term is q1, second term is also q1. Take q1 common and you are getting some big term here. Exactly, it appears the same as the previous case, and then vs divided so q1s by vs is equal to big term likewise. And you no need to do anything actually. In this x1s by fs you can substitute all the values, and x2s by fs also you can substitute all the values. So in this case, in place of x2 you find q2, in case of fs you can write vs, in case of b2 you can write r2, in case of k2 you can write c2, m2, l2, b2 you can substitute with r2, and k2 you can substitute with c2, and so on. So directly you are finding the equation of q2s divided by vs. So that also is possible. Whenever you are converting it into fi analogy, so that a big numerical we will solve maybe the next day, not today. Okay, so such a circuit we will do, and here also you can do it. So this can be taken as a homework also. So this circuit is given, draw the equivalent fi circuit. So whenever you are doing a Fi circuit, instead of this M, there will come a C. In case of this K, there will come, I think, 1 by L. In case of this B, there will come 1 by R, or accordingly you can do that. So whatever is parallel, that will remain parallel in Fi. Whatever is parallel here, that will remain parallel. And whatever is series, that will remain series. And only in case of this FT, it will be, here it is VT. In Fi analogy, this will be IT. So just give a try, and this numerical you can take on your own, or you can solve on your own. If you are not able to do it, you can tell me. Okay, so this is FV equivalent. So I'm giving you a task. I'm not uploading it as a course activity or something, but on your own you can solve and you can email me. So I will see who all are interested and who all would like to do. It don't take more than one page. That is, convert this free body diagram into equivalent FI analogy. So just you have to draw this circuit and write two equations. Very easy. Only thing is, in that case you have to do S into phi S. Okay, is equal to you can say Vs. So in that case, what is there? V is equal to d phi t dt. So input will be I, and this node things, that is this one and this one, they will be actually phi 1s and phi 2s. So in that case, S into Vs, that will be equal to phi 1s. Sorry, S into phi s will be equal to V1s. So V1 is equal to V is equal to d phi dt. Likewise, so I is equal to dq dt for FV equivalent, V is equal to d phi dt uh, FI equivalent, and accordingly you can find out what are the equations. So I think I have I is equal to dq dt. So I think here I have written wrong. So I1s should be is equal to sq1s and I2s will be sq2s because I is equal to dq dt. So please do this correction. So I1s is equal to sq1s and I2 will be equal to sq2s. So that way you can substitute here and you can get the answer. So this was the first numerical for today, and these are the equations they have written. So they have written all the big equations in time domain, and then they have proceeded accordingly. Okay, so there is a second numerical we will see. So this is our second numerical today. Question is the same. That is what we have to do is we have to find out what is the equivalent circuit and what is the FV analogy for this. I have not gone to the end. I have not gone to the FV analogy, but I will see what is the circuit. It is not difficult. First thing you have to say is all the masses are having wheels. Okay, all the masses are having wheels. That means there will not be any friction here. Okay, and this is a rigid. This is a wall kind of a thing. So this is a wall, and where is the force? So force is given to M1, and M1 and M2 they are linked with K2. Okay, so this K1 and B1 they will be having displacement only in one direction, that is x1, and ft will be having force on m2, so there will be a displacement x2, and there is another displacement as x1. So x1 and x2 they are the displacement. K2 is a link between m1 and m2. So it is not difficult. Only thing is directions and all these things are given little bit here and there. So let us first form the free body diagram. So what is the free body diagram? We will find this m1 k1 b1 they will be parallel, and there will be another point x2 and m2 will be there. Force is connected to m1, and between m1 and m2 there will be a series link that is called as k2. So diagram is very easy. Now k1 m1 b1, between x1 and x2 there is k2, and x2 is m2. That's all. And as there are wheels, okay, so as there are wheels between m1 and m2, no extra friction force comes below the m1 or m2 because there are wheels. If the wheels were not there, in that case you had to add another b1 plus bx, and here also you had to add another by. Okay, b1 I cannot say because it is already given. B1 is a element which is in the circuit, that is the damper. Now if the wheels were not there, I had to add another friction. So you could do this thing as b1 plus bx, and here you could say that was a by. Okay, so this bx would have come same thing in parallel with b1, and this by would have come in parallel with m2. So in the free body diagram, in that case, if the wheels were not there, so in this case this b1 would have become b1 plus bx, and in parallel m2 there would have come another parallel thing that was by. So that was the only change. So now you are writing equation at node x1. So this is k1 x1, that is this one k1 x1 plus m1 d2 x1 dt2. Second one, third one is b1 dx dt. Now this x1 k2 into x1 minus x2, because you are writing the equation for x1, so this is k2 into x1 minus x2, that is this term is equal to ft. So there will be 1 2 3 4 5 terms here you are finding with respect to node x1. There are 5 terms. So one term is the input, that is ft is equal to all the dissipations. So dissipation k1 m1 b1 there with respect to x1 and ground, and this k2 actually is connected between x1 and x2, so that's why k2 into x1 minus x2 term is there. Now whenever you are writing so next you can take the Laplace transform, and you can find out the relationship between x1 x2 and fs. Okay, so there will come three main variables, fs, x1 and x2. So fs, x1s and x2s. You cannot find x1s by fs or x2s by fs from there, because now fs is equal to x1 x2 both. So the second equation will help you. What will be the second equation? This will be m2 d2 x2 t dt2 and k2 into x2 minus x1 is equal to 0. So that is the second equation what you are finding here. So this is the second equation. The second equation is m2 d2 x2 dt2. Likewise, and from here if you take the Laplace transform, it will be m2 s square x2s plus k2 x2s. So this is in one side, and right side it will be k2 into x1s. So from this equation Laplace transform you can separate out x1 and x2. So x1 you can represent in terms of x2, x2 you can represent in terms of x1, and in the first equation you can substitute that. So after this, whatever Laplace transform you find, in that you substitute x1 in terms of x2 or x2 in terms of x1, and accordingly you can find out the transfer function of f1s by x1s or f2s by x1s by fs or x2s by fs. These two things you can find out. And then equivalent circuit, equivalent electrical circuit, and all those things. So they are writing all the equivalent nodes and everything. So you can see this is the FI analogy what they have drawn. So this is very important. First case it was the FV analogy, the numerical we had solved. This is the FI analogy. So in case of voltage, there is the current, okay, and wherever is M1, that is substituted with C1, and wherever there was a spring, that is K1, that is substituted with inductor. But only thing is the inductor value L1 will be 1 by K1. Wherever there was a resistance, that will be substituted, sorry, wherever there was a damper, that will be substituted by a resistance, but the value of resistance will be 1 by B1. Again, there was a spring here between first and second link, and this will be substituted by L2. So spring is substituted by L2, but the value of L2 will be 1 by K2. And there was a mass here, and that mass is actually substituted by a capacitor M2. So what we have done is we have written the FI analogy of the given mechanical circuit. But the problem in this case is they have not found the transfer function. They have not found the transfer function of the mechanical system. So you find the transfer function of the mechanical system. That is your first job. Then write the function, transfer function for FV analogy, and lastly you write down the transfer function for FI analogy. So I will ask you these two numericals. So one first numerical is solved actually. Second numerical I will ask you as in your OBA. I will ask this numerical as a solution. So the question will be, whatever mechanical system I give, first find its transfer function, both the transfer function, that is x1 is by fs, x2 is by fs. Then you have to convert it into equivalent FI analogy. Then write down its loop equations, and write down its loop equation in terms of Laplace domain, and then find out the transfer function, that is E1s, sorry, phi s by phi 1s by is, and phi 2s by is, because we know that phi is equal to sorry, E is equal to d phi t dt. So though I have written here E1 and E2, but actually you are supposed to find out the final transfer function in terms of phi 1s and phi 2s. So E1s is equal to s phi 1s, and E2s is equal to s phi 2s, and accordingly you will be finding two transfer function, that is phi 1s by I1s is, and phi 2s by is. So this will be asked in your OBA. So these are the two numericals first what I wanted to do today. Then there are few more numericals we will do. So just let me launch my PDF and we'll solve some more numerical. Yes, so I think this numerical is visible. So from the domain of modeling of mechanical or electrical system, directly I have come to some difficult numerical of block reduction. So block reduction numerical we have done. This is a numerical or block reduction which we are going to solve now. So this is a very specific kind of numerical because it is big. It is looking very small, very flat kind of thing, but actually this results and all answers will be very big. And whatever course activity 3 I had given, that course activity 3 actually you will be getting some help from this numerical. So you are finding that there are mainly 3 loops. So this is the first loop, and all the loops are having feedback gain is equal to 1. That is the first thing you have to find out. So this is the loop negative feedback 1. This is another loop, that is negative feedback 1. This is another loop that is having negative feedback as 1. So all the 3 loops are having negative feedback as 1. This is 1 by R2, this is 1 by SC2. So there is actually a circuit. There is a circuit with 4 components, that is C1, R1, C2 and R2. So I will show you the circuit later on sometime, but that circuit is converted into this block. So that is one type of numerical we have not solved today till yet, but I will show you the circuit. So from that circuit we have drawn the block diagram, and we can solve very easily this thing very easily by signal flow graph. But the challenge is to find out the solution by block reduction technique. So let us do that. What is the first thing? First thing is what we are doing is, so this point we are shifting afterward. Okay, so now whenever we are taking this point up, this 1 by R2 is not multiplied in the feedback, but as we are taking it afterward, so we have to divide this path 1 by 1 by R2. So that will become 1 divided by 1 by R2, so that will become R2. Very important step we have to understand. That is, first thing, we want to remove the entanglement. If we want to remove the entanglement, first thing you have to remove this point after this 1 by R2. So whenever we are taking this point feedback, at that time this gain is not multiplied in the signal. But whenever we are taking this afterwards, in that case what we are doing is we are actually multiplying the signal with the gain 1 by R2, and then we are taking the feedback. That means in the feedback, actually whatever the feedback is 1, so that 1 has to be divided by this gain, and this gain is nothing but 1 by R2. Hence this path, feedback path, will become 1 divided by 1 by R2, so that will become R2. So that is the first step, and then we come to this step. So all other steps remain same. So this is the R2. Now this is one loop, this is another loop. So now this loop is free, you can check, this loop is now free. So if you multiply, the forward gain is 1 by SC2R2, and this denominator, or not denominator, this is HS, actually this is the feedback path, this is having gain 1. So now G is 1 by SC2 into R2, and HS equal to 1. So you just do that, G divided by 1 plus GH, 1 plus GH, because it is negative feedback, and what you will be getting is 1 divided by SR2C2 plus 1. So up till that there was no problem. One takeoff point shift we have done, and we have got like this. Now there is a big problem. Now big problem is now there is an entanglement. Okay, so entanglement is like this. Now what can we do? This point, this takeoff point, we can take afterward. Okay, so this takeoff point we can take afterward, and whenever you are taking this takeoff point afterward, what's happening is this part, this gain, actually this gain has to be divided in the feedback path. That means whenever this signal is coming here and we are taking the takeoff, this gain 1 by SR2C2 plus 1, this is actually not a part of this feedback, because this feedback is being taken before this gain. Okay, but whenever you are taking this point afterward, in that case first the multiplication is happening, and then you are taking the feedback. That means this feedback path has to be divided with a gain of 1 by SR2C2 plus 1. So if you are doing that, 1 plus SR2C2 comes at the numerator. So you can find it. So 1 plus SR2C2 has come at the numerator, and now everything is very simple. Okay, so now this part, if you multiply, and its a forward gain is 1 by R1 into 1 plus SR2C2. So denominator will be R1 into 1 plus SR2C2, that is a denominator, and feedback gain is R2. So now this loop is simple. If you solve it, something like this you are getting, and this multiplied by 1 by SC1, and then this is the feedback path. So if you're solving all, then what I'm getting is 1 by SR2C2 plus SR1C1 plus SR1 R2C1 plus S square C1 R2, so all those things. So what is the main question is, what is the order of the system? So whatever transfer function you have found, you can check that denominator is having highest order of S as square. That means this is a second order system. Can you confirm it from the circuit? Can you confirm it from the system? Yes, the system is having two capacitors, C1 and C2. So they are the energy storing element, and R1 and R2, they are not energy storing element. Okay, so only capacitor and inductor, they are energy storing element. In this circuit there are two energy storing element, hence the denominator of the transfer function, this is having a square. So very perfectly it is, and you are finding that this thing is actually having a second order system. That means there are two energy storing element, and circuit we have seen, this is C1 and C2. So whatever the circuit is given and whatever we have found, this thing is in the line. So this is a very important numerical what we have seen, and there is another numerical what we are going to see after it is this. So this is actually more important, and this is more complex. So this is my note, and I wanted to show you mainly the second numerical number 15. Be very careful, because lots of processes are there, and this is a total entanglement, and we have to remove the entanglement. So you are finding that this G3 G4 loop, this is G3 G4, this is not a loop, this is actually a forward path, but this forward path is actually entangled by this H1. If this H1 was not there, directly I could write G3 plus G4 G4, but this H1 is now there. Okay, so how to remove this entanglement? This is not easy. Okay, so first thing what we'll do, I think this H1 have to be taken before this. I think that will be the first step. So take this, see this diagram, and G2. What is this G2 called? See that it is going from the input directly, it is going to the output. So whenever we do state space, I will refer to this diagram. That is, remember this numerical number 15 from my notes. This will be the case for direct transmission matrix. So just know this much now. When we go to the module number 5, when we are doing state variable analysis, at that time there will come a D matrix. And what is D matrix? It is called as a direct transmission matrix. So hardly we find any kind of industrial system where the input is directly processed and given to the output. So this is not very easily found, but in this case we are finding it, that is input and output directly connected by a factor or gain factor of G2. So this is also a forward path. So this is a forward path. This is another forward path, that is G1, G5, G3. There is another forward path, that is G1, G5, and G4, and all these things. So there are actually 3 forward paths. If you are doing it by signal flow graph, it will be very easy. So you'll be finding block reduction technique is little difficult, cumbersome, calculation becomes big. But the same numerical, if you are doing it by signal flow graph, it will become easy. Okay, so how many forward paths are there? So one forward path is G2, another forward path is G1, G5, G3, another forward path is G1, G5, and G4. We are finding it, and there are feedback paths. This is H1 negative feedback, and this is H2 negative feedback. In exam, if it is not given any sign, you have to take positive. If negative, the sign will be mentioned. Now check what is the first step we are doing. So first step, they have done the same thing. You are finding that this G3 has been taken before, or this point has been taken afterward. What we are doing is, so this G4 point has been taken afterward. Okay, so this G4, so this point has been taken afterward. So what we are doing is, so first, from where are you taking the G4 point? G4 point you are taking actually before G3. But if you are taking this point afterward, means actually you are multiplying the system and then taking the feedback. That means the signal is getting multiplied with G3. That means G4 has to be divided by G3. So that is what we are doing. So G4 by G3. Okay, now this becomes a forward path and with 1. So this is a very important step you are finding. I will explain again. Here, whenever the signal is coming, so from G5, whenever signal is coming, I am directly taking it to the forward path in the forward direction. So this signal from G5 is not getting multiplied with G3 and then forwarded. No. So G5 output is getting divided. One is flowing through G3, another is getting forwarded to G4. But if I'm taking this point after G3, in that case, the signal from G5 is getting multiplied with G3 first, and then I am taking the it out through the G4. That means I am getting more signal at G4, that is multiplied by G3. So how can we compensate that? Whatever is the gain of G4, I have to multiply it by G3. So this is the way you have to understand it. So everything else remains same. So the top one becomes H1, the bottom one becomes G4 by G3. Now this thing is G4 by G3 plus 1. So that is what you are getting here, G4 by G3 plus 1. And this part is actually multiplied. So this is G3 G5. So this loop is now not entangled. So this becomes G3 G5 divided by 1 plus H1 G3 G5. So that is this one. And G1 is also getting multiplied with it. What we are finding is G1 into G3 into G5 divided by 1 plus H1 G3 G5. That is this part. So what is this part? This part is nothing but this whole part. Okay, this whole part. Okay, and this part, 2 forward paths are getting multiplied with 1 plus G4 by G3 likewise. Okay, so I don't think there is any problem here. So there was only one point, that is the this forward path was, this takeoff point was after G5. Now you have taken it after G3. Okay, so one step ahead you have taken it, one step right you have shifted, that is shifting the takeoff point after the gain block. This is what you have done. So after that, you are finding everything becomes easy. So this thing is 1 plus G3 G4. This thing becomes H1 by 1 plus H1 G5 G3. That is multiplied with G1. So now these two things are here. Till now there is no problem. Okay. So now this is the path where there is no problem. Now what is there? So now again you are finding that there is an entanglement. What is that entanglement? What you are finding is there are the 2 loops. Okay, so this loop is starting outside and getting finished inside, and this loop is starting outside and getting finished inside. So now what you can do is we can swap, okay, or we can shift these 2 gain blocks afterwards. So what we have done is, whatever was the forward path of G2. So you can see that this is the input and this is coming here, and this was getting here at positive. So this is actually a forward path which is added here. What I'm doing here is now I'm shifting this point, I'm shifting this point before this block. So there's a single gain block. Okay, you can multiply it and it will be what? So this G3 comes denominator, G3 gets cancelled, so it will be G1 G5 multiplied by G3 plus G4. So you can find here G1 G5 multiplied by G3 plus G4 divided by 1 plus G3 G5 G4, G3 G5 H1. So divided by 1 plus G3 G5 G1. So if you are multiplying these two, what you are getting is this one, G1 G5 G3 plus G4 divided by 1 plus G3 G5 H1. So this one. So there is a gain block. What I'm doing is this summing point I'm taking before. So shifting the summing point before a gain block. We have done it, and if you're doing it, what we are finding is this G2 has to be multiplied or divided accordingly. Okay, so as we are taking it before, so all these things are getting multiplied, and then coming here, what we are doing is we are taking it before. That means whatever signal is coming here, that will get multiplied. That means here we have to divide it. So G2 has to be divided by this G5, that is G1, G5, G3, G4 divided by 1 plus G3, G5, G4. That means it is reverse what you are finding here. Okay, so whatever gain you find here, so multiplying this to whatever gain you find here, 1 upon that has to be multiplied with G2. That means G2 has to be divided by this gain. That is what we are finding. So this is the most important step, and there is a page change also. So check this step. This is very much important. That is, I'm shifting this summing point before this single gain block, though it is looking double, but actually it is single, and the value of it is G1 into G5 multiplied by G3 plus G4, that is the numerator, divided by 1 plus G3 G5 H1. So this is the value. Okay, now there is a single gain block, and now whenever you are swapping, or now whenever you're shifting this summing point 2 before this single gain block, actually you have to divide this G2 by this forward gain. That means just flipped it. So 1 plus G3 G5 H1 divided by G1 G5 G3 G4, like this. So this is the step which is very important, and after this what you can do is you can find that there are two summing points which are amne samne ho gaya. That means these two summing points, they are in front of each other. So what we can do is exchange the summing point. So you can find this step. Okay, and after that you can exchange the summing point. That means this summing point with this input will come here, and this summing point with all this H2 input will come here. So this is the second step. And after doing this, you are finding that the entanglement is gone. So here the entanglement is there because this loop is starting here. There's a forward path, not loop, I'm sorry. So this is a forward path, it is here, and this is a loop, and inside this loop there is a summing point coming. But when we are finding that two summing points are in front of each other, in that case we can swap the position of the summing point with their respective input with it. So suppose this was SP1, this was SP2. Now I am drawing SP2 first and SP1 next, and you are finding that in the above diagram SP1 was having a negative feedback with H2. So now SP1 is this one. So SP1 is having a negative feedback with H2, and SP2 is having positive directional forward path with gain of G2 into 1 plus G3 G5 H1 divided by G1 G5 into G3 G4. So the same thing has come here. Okay, so now what you are finding is both the loops are not entangled. So here these are the two forward paths. So 1 plus this whole gain. So this gain is equal to 1, and this gain is G2 into 1 plus G3 G5 H1 by G1 G5 G3 plus G4, that you are writing here. So this path is having gain 1, this path is having this big gain. So this is the first part. And now this part is the forward path, and this part is the feedback path. So G divided by 1 plus G into H2. This is what you have done. And now these two paths are coming multiplication. So they are called as cascade. Now you multiply them, and this is the final transfer function. So very important a diagram that is there. So these two numericals you just practice, and you can get it done properly. And this circuit, okay, so the numerical can be, I will give you a circuit first. From there you have to draw this block reduction block, or this block diagram, and you can solve it. So answer you know. Next step will be convert this thing into a signal flow graph, and after finding signal flow graph you can find out what is the answer of the signal flow graph, and you will find that answer of the signal flow graph will come within half a page. But block reduction is a little bit bigger answer. so that you can find, but it is not very big. Actually answer is given, and the main thing to observe is here denominator power of s is actually s square. That means there are, it's a second order system. And how can you justify that? Because in the circuit, whatever block diagram is giving, there are two capacitors, that is C1 and C2, you can find. So there are two energy storing element, hence the denominator is having power of s as square. Okay, so these are two numericals which I wanted to show. Now we will go for another numerical, and which is also very important. Let me launch, and let me launch that numerical. What is that? That will be something called as if there are more than one inputs. Okay, so if there are more than one inputs to a system, how can we find transfer function? So in that case, we'll be finding there are different types of transfer function which are possible. So the numerical is not difficult, but it's a new type of numerical, hence I would like you to do that. So just let me launch it, and it will be a MIMO system. Okay, not MIMO, I cannot say multiple input is okay and single output. So you can say it's a multiple input single output system. Then how to solve it? How to find its transfer function? And you'll be finding there are more than one transfer function possible. So I will solve it for you, and exactly this kind of numerical is given in our book of M. Gopal. So that I will give you as a homework. I'm having the solution for that also, but the solution you have to do. But here I'm finding there's a system where C is the output of the block, and there are four inputs you are finding. Okay, so what are the inputs? R1 is the input, R2 is the input, R3 is the input, and R4 is the input. Okay, now you can find out four transfer functions here. One is C by R1, another is C by R2, another is C by R3, another is C by R4. How to find it? Simple superposition theorem. So it is written here that apply superposition principle, uh, one a source at a time. So if you ask me, sir, how to find the output? So output can be found by one source at a time. That means C by R1, one transfer function, then C by R2, then C by R3, then C by R4. So what to do to the other sources when one source is taken at a time? Suppose here I'm saying that I want to find C by R1. In that case, R2, R3, R4 take as 0. This is a very simple way. Whenever you are trying to find out the transfer function of C by R2, take R1, R3, R4 as 0. C by R3, in that case R1, R2, R4 as 0. And C by R4, in that case R1, R2, R3 take as 0. Okay, so likewise. So all the four circuits, the system will change them. So as soon as you are making that, suppose you are trying to find out C by R4, in that case R1, R2, R3 are taken to be 0. That means all the loops and everything will change. So as soon as you are taking the R4 as the input, this H1 will come as a forward gain. I will draw the circuit and I will show you that if you are taking R4 as an input, in that case this is the feedback path. So from C to this, there's a feedback path, it's a positive feedback, and this H1 actually goes to multiplied with G1. So in that case this summing point is not there because R1 is equal to 0. So H1 with minus and G1. So this sign is very important. So whenever you are taking R4 as the input, in that case feedback is this one, it's a positive feedback of value 1, and this H1 with minus will get multiplied with G1. So forward path gain will become then minus H1 G1, and this summing point is of no value now because R2 is not there. This summing point is also of no value now because R3 is not there. So only one summing point will prevail here in the forward path, and this is actually the input. So there will be two summing points when R4 is the input. That is R4 is the input coming. This is the set point now. This is the feedback point. This R2 summing point will not be there. R3 summing point will not be there. And minus H1 G1 gain will come in the forward path. And H2 will be a negative feedback. And be very careful. What is the symbol of the input? So here, whenever R3 is coming, this R3 is coming to be negative. So this itself is actually, this is not R3, this should be minus R3. That means this is actually inputting a negative base in the signal, in the system. Likewise, so R2 is positive, R1 nothing is given, this is to be taken as positive, R4 nothing is given, this is also to be taken as positive. So let us do it. We can find out four transfer function. First one, C by R1. Okay, so whenever it is C by R1, see that circuit has become very simple, our system has become very simple. So in that case, R2 we have made 0. So after G1, nothing is drawn. R3 we have made 0. So after this, so here before G2, there was R3. So nothing I have shown. G2 is there, H2 is there, negative feedback. R4 is not there. So whatever is the positive thing coming, this is positive, positive, H1, and this is negative. Now this is a very simple circuit. You can find out what is the transfer function. That is this thing, this loop you solve first. So this will become G1 into G2 divided by 1 plus G2H2. So first you solve this, G2H2 divided by 1 plus G2H2 multiplied by G1. So likewise we are finding this, and then H1 is the negative feedback path. So what you are finding is C by R1, or you can say C by R1, that is output by input. So output is always C. So C by R1 is equal to G1 G2 divided by 1 plus G2H2 plus G1 G2 plus there may be some other term or something. You just check on. Okay, so that will be the first term. Whenever you're doing it, what will it be? So this is G1 G2 divided by 1 plus this. So 1 plus G2H2 plus G1 G2. Here the H1 term should be there. It has gone missing due to scanning. Please find it here. So this will be G1 G2 and H1. So that H1 has gone missing here. Please correct it. So this is the first case. So this is the output for source 1. Okay, finally what we'll do is, so we'll find 4 outputs. So C for source R1, C for source R2, R3 and R4. All those 4 C's we find. Okay, so all those 4 outputs we'll find for source R1 acting alone, source R2 acting alone, source R3 and R4 acting alone. Then final C is nothing but addition of all this R1 multiplied by the transfer function. So that will be the final output. That is C is equal to part of R1 plus part of R2 plus part of R3 and plus the part of R4. That is it. Okay, now let us see when R2 is functioning. So R2 is functioning means first R1 we have to remove, and this H1 and G1. So this will become minus G1 H1. So just check what it is. So just check. So this R2 is there, and this should be actually minus G1 H1 because there is a negative symbol, and this is being shown as a plus. Why this is being shown as a plus? Let us see. Okay. So this should be actually minus. This R2 is there, and this is minus H2. So H2 is there as minus, no problem. So H2 is there as a minus, and like this. Okay. So here I think there's a mistake. Please correct it. So this should be minus G1 H1. Okay. So that is one thing. It's a small mistake, but it should be considered. So here this thing is coming as positive. This H1 is coming to be negative. You can remove this part. You can make the R1 as 0, but you have to consider this H1 symbol. Okay, so this actually should be G1 into H1 minus. That's a mistake I have made on my part. Please correct it, minus G1 H1. So this becomes now the system, and now there are 2 loops. So G2 H2 is the first thing you have to solve. That is G2 divided by 1 plus G2 H2, and then this is also a negative feedback. Okay, so accordingly you can solve and you can find out what is the output. Okay, so I think there will come some negative here. Okay, so this also will become, so C is equal to R2 into G2 divided by this. So how to do it, that you see, if there are small mistakes of minus plus, you can correct it. That is there. Now R3 I am taking into consideration. See here, this minus 1 has been taken. So the same thing had to be considered in the previous case also. Just check whether it is done properly or not. So this minus should be there. So whenever H1 is coming, this minus 1 should be taken, and that should get multiplied with G1. Likewise. Okay. Now third source is R3, and then whenever this R3 is there, so in that case minus G1 H1, so it is coming. So you can find here, this is H1 G1 minus, and it is positive, but it is coming to be negative. So you're finding that here it is coming. So there's a feedback path now. This is G1 H1 with negative feedback, or minus G1 H1 with positive feedback. Now this summing point is nothing but this summing point. Okay, so R3 is coming here. So these 2 summing point I have made same, because there are 2 summing points side by side. I have made them same. So this negative only, so this negative R3 negative, this I have done here. Okay, so this is the only summing point. So whenever 2 summing points are side by side and this thing is having 1 input, you can mix them also. Okay, so this R3 is coming to be negative to this, so this R3 has been shifted here. Okay, and to this summing point, H2 is coming as negative, so H2 is coming as negative, and this H1 G1 is also coming as negative. So what I have written is minus H1 G1 coming as a positive. That means H1 G1 is coming as a negative. Likewise, and then G2 H2 is the loop, forward loop, and G1 H1 is another bigger loop. So directly if you are solving, solving is not easy, only understanding and reducing it to actual block. That is the main job. But one problem is there. You're finding that R3 is negative. Okay, so you're finding that R3 is actually connected to in the negative mode. So R3 is in the negative mode. That means whenever you're finding, so inside it, inside this, everything is positive, because this is a negative feedback and this is minus, positive means negative. So everything is denominator should be all positives, but this R3 is actually multiplied with minus. So C is equal to minus R3 multiplied by this transfer function. So transfer function is all positive because everything is a negative feedback. So G2 by 1 plus G2H2, G1 H1 G2, everything is positive. But as R3 is negative, C is equal to minus R3. So now what we have found out is C is equal to what part of R1 is coming at the output, what part of R2 is coming at the output, and what part of R3 is coming at the output. All those things we have found. Last one is R4. So whenever R4 is there, this is the input which is coming. So I had shown you initially. So 2 pages back, I'll go back 2 pages. What I'm finding is this is the R4. So check the main numerical. Okay, so this is the R4 which is coming. This is the R4 which is coming, and in that case, H1 G1 minus, that will come in the forward path. So H1 G1 minus will come in the forward path, and then this R3 will not be there. This summing point, R2 summing point will not be there, and only this G2 H2, this loop will be there. So only there will be this loop. Okay, and there will be a feedback path of gain 1, that is a positive feedback, and forward path will be having a gain of minus H1 G1. So let us see whether we have done it properly or not. Okay, so this is the R4 input. Whenever it is coming, check. R4 input is coming. This is minus G1 H1, and this is G2 H2, and this is the feedback path with a positive sign. And that's why it will be a negative here in the denominator. So it should come accordingly. So just check. And there is a minus thing. So just see, the calculation is not difficult. You can find it out. Now final C. So what you are finding is C is equal to this. Now the final C is C into R1 plus C into so whatever you have found, C into R1 into transfer function in the first case, that is C by R1. So this is the second case with R2. This is the third case with R3, and this is the fourth case with R4. So there might be some mistake of symbols and all this thing, sign, you can correct it. But this is the way you are supposed to find out if there is more than one inputs, then how to find out the transfer function. So this is a very important numerical, might not be asked in the exam, but you should not get bogged down if more than one sources are asked, and if you are asked what is the transfer function. So here we are not finding transfer function actually, we are finding what is the output, and in the output you are finding R1, R2, R3, R4, all the inputs are there. I think I missed the R4 thing. So this G1, H1, G2 into R4 should come here. So there should come a R4 term here also. And one important thing is, I think denominator is same in all the cases. Okay, that you are finding denominator is same in all the cases. So 1 plus G2H2 plus G1, G2H1, this is the denominator that is common for all the cases. And G1, G2, H1 into R4, it should be there. Okay, so that is actually the output C. So this is another numerical which I wanted to show it to you. And now the last thing, that is if there are more than one sources. So if there are more than one sources, then exactly how to find the transfer function, and there is a numerical on that. So that you will find, this numerical you will find in the book of M. Gopal, I think page number 117 or 118. Just check, and you have to solve for this. Okay. I think now my notes is visible. And what you're finding is here, this is a multi-input single output system. So the same numerical just now, whatever you have done, same kind of a thing. So this is a RS, this is a set point input which is coming and flowing through G1, G2, G3, G4 and all. And this is WS. WS is nothing but, you can say it's a disturbance, or it can say it's another input. Okay, so this is going towards G6 and coming here, and this is going towards G5 also. So the same input is having two parallel paths. One is flowing through G6 and is flowing through G5 and coming at the output. So what is written here? So consider another typical block diagram showing 3.18. So this is the diagram. This feedback system has two inputs. We shall use the superposition to treat each input separately. The Mason's-Gain rule may be applied directly to the block diagram without transforming it into an equivalent signal flow graph when the disturbance input WS is 0. So superposition means consider one source at a time and consider the other sources equal to 0. So whenever you are trying to find out ys by rs, in that case you have to just take that this input is equal to 0. So whenever I'm saying this input is equal to 0, then this is G6S, this is G5S. They are actually in the kind of a reverse kind of a mode you are finding. So just find out how can you solve it. Okay, so this is G6S, this is G5S. So this both will come in kind of a series. Okay, so this both will come in kind of a series, and as there is no input here, just see how will you solve for it. Okay, so when the disturbance ws is 0, the resulting block diagram has one forward path and two loops. Okay, so what is one forward path? So this is the one forward path you are finding, and two loops means this is the loop. Okay, so this is the loop, this is one loop, and this will be another loop, this will be another loop. Okay, likewise, and this part I think it has to be removed because there is nothing here. So ws is 0 means nothing is coming to this, so this is 0 into gs, nothing is coming. Again this is 0 into g5, nothing is coming. So whenever ws is 0, I think g5 and g6 should not be there in the transfer function, so you are finding the same thing. Okay, so ys by rs, whenever you are finding ys by rs, ws is equal to 0, in that case you are finding in this transfer function there is no mention of g5 and g6, because the g5 and g6 they are actually going reverse, going in the opposite direction. So ws is coming, this is g5, ws is going, this is g6, and as ws is 0, there is no mention of g5 and g6 in this transfer function. So you can find out this transfer function is comprising only g1, g2, g3, g4, h1 and h2. So g1, g2, g3, g4, g3, h1, g1, g2, g3, g4, gh2. So whenever you are finding ys by rs, in that case there is no mention of g5 and g6 that is there. And in the second case, when rs is equal to 0, the block diagram has two forward paths and two loops. So whenever this rs is equal to 0, so there are two forward paths. So this is one forward path, ws to g5s to g4. So you're finding this one, g5 into g4, and there is another forward path, that is g6 into g2s, and it is going like this. Okay, so there are two forward paths, and in that case I think g1 is not there anywhere. Okay, so you are finding that g1 is not there anywhere, so just find it out exactly. So whenever this rs is equal to 0, redraw this diagram exactly how it happens. So make rs is equal to 0, so this loop will be there. So there are two forward paths and two loops, and the two loops touch each other, and both the forward paths touch both the loops. By Mason's-Gain rule, you are finding directly like this. So first I would like to ask you to solve this by block reduction technique, and then by Mason's-Gain formula. So what you are finding is ms ys by rs, and then mw ys by ws, finally the response. So what you are actually supposed to find out is ys. So ys will be equal to ms into rs. So there is the first thing. So from here you are finding ys is equal to ms by rs, ws is equal to 0. So there is the output for first source. And for the second case, ys will be equal to ms into ws. That means this ws you have to take right side, the whole thing multiplied by ws will be ys when the source of ws is in action, and ys will be equal to rs into this whole transfer function when the source rs is into action. So below is the ys when ws is into action, and above is the rs is into action. So if you add them, it will become y is equal to ms rs plus ms mws into ws. So this is a numerical you have to solve by two methods and find out the ys. So one by signal flow graph, another is by block reduction technique. So you will find it in page number 117 in the book of M. Gopal. Please solve this. That's all from this lecture. So some more numericals we'll be solving in the coming two lectures in this week, and we are going to see all the typical types of numerical for module 1 and module 2. That's all from my side now. Thank you.